Hi everyone, welcome again to another episode of the Focus on Geothermal webinar series. This is a partnership of ThinkJ Energy and Enerchange, and today we're doing this in a very unusual schedule for this webinar series because I think this is the first time that we're having a speaker from New Zealand, and it's very unusual and it's kind of a miracle of scheduling and compromising, but here we are, we made it. It's our pleasure today to have Isabelle Chambefort from GNSI. She is the Energy Futures team leader, and she is a geothermal geoscientist with more than 20 years of experience in geothermal ore deposits and petrology research. Her research focuses on the magmatic hydrothermal geochemical transition in arc systems. She also led the recently completed Geothermal, the Next Generation program, which explored New Zealand's supercritical resources and successfully secured $60 million in funding from the New Zealand government to explore supercritical technology and its potential as a baseload solution. I would also like to remind the audience that you can write in your questions at any time. There should be a questions tab in the webinar panel, and we will get to those questions after the presentation. And it is my pleasure to welcome Isabelle. The floor is yours.
Thank you very much, Carlo. Welcome, everyone. Thank you for the invitation and thank you for joining on this unusual hours. It's always challenging when you are based in New Zealand. You have to adapt to the time zone, I would say. So thank you very much for joining today. It's an absolute privilege today to talk to you about some of the research we've been doing and pushing for more than a decade now in New Zealand. And this is not at all my only doing. It's the entire team and the New Zealand sector that have been supporting and pushing some of this research that I will present today. So let's just go straight into it. Today, I'm going to talk mainly about superhard geothermal, a baseload energy solution for New Zealand. As we all know, we have a little bit of a problem. We absolutely must transition from fossil fuel in the coming years. This is becoming an emergency. We're going to see more and more large climatic effects, and we need to find some solution. We, as geoscientists, we have a responsibility because of our intrinsic knowledge of the Earth to find some solution that can support this transition, but in a way that it is easily conveyed to decision maker. And this was really the final step of this research I'm going to present today, is showing you how we gather a team of multidisciplinary researchers to get into government, to get into policy, to acquire some support and to provide fit for purpose solution for New Zealand. So as I was saying, we need to drastically adapt our energy system to limit emission. There is no difference from New Zealand, despite the fact that we are on the other side of the Earth. We have a 0% carbon emission energy system target, and it will be done by electrifying New Zealand. There is some intersect challenge in New Zealand as we are far away. We are an island, so we're extremely dependent as well on the market and where the electricity can be sold. But New Zealand has a target of doubling the renewable electricity by 2050 to support the growth of the electricity need for the country. But to do this, we need to also manage the reliance on other renewables such as wind and solar, and provided some solution for a 24/7, 360 days of electricity per year. And that's where geothermal is really important for New Zealand. It's a long tradition in New Zealand to have a geothermal development, and we're just continuing on this historical legacy. New Zealand has an amazing tectonic setting where heat flow is coming at the surface more or less all over the country. It's very tectonic. We are the merging between two tectonic plates. But in the North Island, where most of the geothermal system are actually already utilized, we have this amazing zone that we call the topovolcanic zone, which is a combination of a volcanic arc and a rifting of this same arc, which created one of the highest heat flow in the country, a large amount of magmatic product. For, in comparison, the amount of volcanic product that was distributed in the last 2 million years in the North Island of New Zealand is equivalent to Yellowstone. So it's an incredible heat machine that we've been utilizing with great success in the past. But can we utilize this system a little bit better? As I was saying, the electricity generation in New Zealand is composed of 20% of geothermal. These numbers are showing 17% and does not account for the new power station that was developed on the Tauhara geothermal field. But so now we are on 20%, and there's definitely some investment as well going into conventional geothermal. The sector is looking at developing new fields. So it's really important. Most of our generation is, renewable generation is using hydroelectric power. We also have a growth in wind and solar in New Zealand, but we still rely a lot on fossil fuel, despite the fact that we are at 86, 90% renewables, depending on the moment of the year. So which is just a challenge, because you need to maintain the growth at the same time as maintaining the peak performance and the load on the system. But due to the growth of geothermal, the growth of electricity demand, we really need to find the correct balance for New Zealand. And that's where geothermal has to play a role. So we not only, for our baseload, is not solely dependent on the amount of hydroelectricity. We need to prevent the future of potential really dry year, and geothermal can provide this solution. In New Zealand right now, in the topovolcanic zone, there is seven sites that are producing electricity, and we are in the top 5,000 megawatt electricity generator in the world. And we're continuing growing our geothermal assets. Most of you, if you are familiar with geothermal, you will know and recognize some of those fields that have been developed, for some of them for more than 60 years, such as Wairiki Power Station. The limitation that we have in New Zealand is that some of those geothermal fields that are located in the topovolcanic zone are actually protected, and we do not want to utilize them to generate electricity. They are treasure, tonga, for New Zealanders, and it would be ridiculous to use those systems, to say the least. So it was really important to find where else can we develop efficient, high temperature that can provide a large amount of electricity to the grid without utilizing the system. So the solution was to look a little bit deeper. Can we utilize some fluids that are deeper in the crust, that are at temperature and pressure, maybe mainly temperature, above the critical point of water, to enhance the electricity and the energy output of some of this field? And so I like to introduce the next generation of geothermal power for New Zealand. In the last decade, and particularly in the last 5 years, we have been gathering a large amount of geophysical, petrological, volcanology, geochemistry on those geothermal fields to better understand what is the heat source, the heat transfer, and the location of this hydrothermal plume that are hit from water that are heated up from the magma source towards the surface in the topovolcanic zone. As I was saying earlier, this is an amazing place on Earth, and we are extremely privileged to work in this geological wonderland, if you want. And so I will present today some of the results that we have been doing. And I want particularly to emphasize and thank the Geothermal, the Next Generation team, who has been incredible. This is more than 30 scientists, PhD students, master students, planners, Kianga advisor. So we covered really from large exploration, geochemistry in understanding the thermochemistry of supercritical fluid. But what a key aspect of that was that can we integrate all of our geoscientific knowledge and translate it so we can provide some report and we can provide some economic feasibility to the decision maker so they can actually invest in it, de-risking the future of a new phase of geothermal exploration for New Zealand. Not just the sector, the entire New Zealand society was really at the core of this program. So I'm going to present first some of the, mainly some of the results that we've been looking at. So what we have been doing, we try to understand where the heat is and where is the large scale boundary between the brittle ductile transition, magmatic system, and those hydrothermal plume, the system that we already utilize. It is always challenging when you don't have a direct access. So we were really relying on some of the geophysics for that. And we combined magnetic, gravity, seismic, magnetotelluric to better understand large scale of the entire crust. So it's really understanding and imaging the crust underneath this incredible volcanic province. So here an example of the depth to base of the magnetization of the rocks based on magnetic. And we can see here that you have a very high heat flux and demagnetization of the rock, or magnetization, sorry, of the rock in the location of a central TVZ. This, you can see the depth of magnetization is really shallow underneath the TVZ. This is not a surprise, but we can combine all of this result with a more regional scale to better understand where we may have magma, where we have fluid in the crust. Another example is doing some new development and new coding in seismic interpretation. So here an example that's prepared by my colleague Stephen Bannister of just a cross section of the VP in the crust with the seismicity event, where we can identify zone of partial melt and in different aspect in different location in the crust. And as you can see, we have some zone of partial melt really shallow in the crust, below 5 kilometers. And you can see really the cutouts of the seismicity where you're actually losing some of the seismicity event, and where we infer that there is a zone of partial melt that can create, obviously, provide a lot of heat, and then being the direct source of where the fluids are heated up and coming at the surface. And most of the topovolcanic zone seismic event, it depends on the location. They stop between 5 kilometers, like at this example here, 4.55 kilometers. Obviously, there is an error into this, or a range into this, to some zone at 10 kilometers. The average brittle ductile transition is estimated to be between 7 and 8 kilometers underneath the entire topovolcanic zone. But we do know that we have some large or probably some shallow intrusion coming at shallower depths. And those are really becoming the target for our exploration. This is an example right here. To better understand what will be the constraint of drilling beyond the seismic point, beyond the known, we need to understand the geometry of the crust. And that's why we've been looking at the basement. And it's really hard, again, to have an idea of what is the geometry of a basement of a structure underneath the known drill area because we do not have a direct aspect. So combining some gravity, combining some petrology on crystal rock, metamorphic rock that are erupted as lithic in volcanic product, we were able to constrain broadly, to constrain what kind of terrain we're going to have. And then we can use this terrain to characterize the fracture pattern, to characterize the mineralogy, the reactivity of some of those rock. And this has been ongoing for several years. Obviously, it's always challenging, but the team has been able to identify that what kind of basement rock we will likely intercept by drilling deeper in the topovolcanic zone. We, as I was saying, to constrain the geometry, we also look at a more regional scale focus on the intersection of several geothermal fields to try to really constrain. So this is a gravity work that has been working. We've been working with Mercury Contact Energy to access some of their data, if you want, to constrain the geometry and the rock at the where we know where it's drilled. And we've been able to revise the structure of where the Grey Waikiki, the basement rock of New Zealand, could be at greater depth. And this is really important to constrain future drilling and to constrain where is the best target, particularly in terms of intense faulting that we have in this volcanic rift, if you want. To go a little bit more in detail as well, what we've been doing, and a team of structural geologists has been looking at surface sample and downhole sample and fracture in the Grey Waikiki rock. So we have an understanding of what is the fracture network of this basement rock. So we can advise and we can provide some constraint on what will be the rock that we're going to drill. This has also implications for any future geothermal, not only supercritical, as the fracture network could be reactivated during thermal stimulation, or even future, maybe, who knows, EGS development in New Zealand, enhanced geothermal system in New Zealand. So that was really a key, is to go from this large regional scale to down to outcrop, to really try to constrain what is the fabric of the basement crust in the topovolcanic zone. There's a lot of work that's been going on the volcanic product and the petrology and the magmatic system. So we were really looking into integrating this entire geoscientific knowledge to do this. To continue some of the work that we've been doing in igneous petrology, we try to constrain from a magmatic point of view if there was any deep circulation of meteoric water that influenced the composition of a magma, or that show that the magma interact with an hydrothermal system. So we had a postdoc, Shane Royaker, that worked on oxygen isotope in different settings, in caldera forming, looking at where is the dynamic between when you have a magma forming in New Zealand, does it assimilate so hydrothermal altered rock? Does it not seeing any hydrothermal effect or not? And what we show is that the caldera actually, some of the stage of the caldera don't necessarily interact, but it's because we have a lot of caldera event in New Zealand all the time, you're developing an hydrothermal system above it, and the new magma that are generated could have assimilated some hydrothermal rock. And it's a broad scale, but it's really to try to combine that with igneous petrology barometry. We can more or less say that the groundwater, if you want, that infiltrate the topovolcanic zone is at least, it's going quite deep. It's not limited to the 3 kilometer. It's also assimilated by the some of the volcanic rock that are erupting in the topovolcanic zone. We put all of this information into a numerical simulation. And we collaborate with the ETH Zurich, with the team of Thomas Ressler, to try to understand. We know we have large magnetic system. We know we have shallow intrusion. So understand where the supercritical envelope could be. It is challenging in New Zealand to constrain if we have supercritical, because we have a brittle ductile transition that is strongly influenced by the heavy silicic rock. So we do not have the same condition, for example, than in Iceland, where it is basalt. So it's not as optimal maybe, but because we have such a large amount of heat, we really needed to constrain what is the best geometry. So this is just a synthetic diagram of where we are, but we have been able to locate this. We also did some of the numerical simulation in a more like large scale to better understand the effect of this deep mush on the dynamic of this hydrothermal plume. And what we show is that over a period of time, you can have variability in your permeability pathway above the hot plate, if you want, which is not necessarily geologically representative of the condition of the TVZ, but it was really important to understand the in and out, if you want, the waving and dying of some of this hydrothermal system, to know if we are in a very dynamic transient condition or if we are in a normal, more stable condition. At the human scale, it's generally pretty stable, but New Zealand is full of surprise and things can change quite quickly, but it's been quite stable for 60 years now. All of that pointed out to another, like some simulation, and we know we have been able to model that we will have supercritical envelope above shallow intrusion that are, so here you can see the temperature condition. If you're looking at the white envelope here, that is your supercritical condition at the basement. The depth of the basement and volcanic field play a certain role. The amount of heat providing by the deep mush is also playing a role, but shallow intrusion are really a key. So integrating that with those model has been constrained as well by the depth of some magnetotelluric anomaly. So we were able to show that, yes, there may be some place on the TVZ where we have the best permeability condition to have a supercritical fluid envelope. And that was really a key for the exploration team to be confident that we should continue some of those efforts. But we haven't stopped there. We've been extremely lucky to be able to invest in a one-of-a-kind flow-through supercritical reactor. And this is my colleague Peter Randall showing the super reactor. And we were able to simulate water-rock interaction for supercritical condition. Why this is important is because both experiments are extremely challenging first, but it's also really important to understand what are the chemistry conditions we're going to intercept by drilling to limit, first of all, the risk in developing some of this field, but also better understand how we're going to manage the system. And it's all start by understanding some of the solubility of this field. So the team has been revising the quartz solubility and revising, here an example, the anotherite solubility at those conditions. Those fundamental chemistry thermodynamic data are essential to model accurately the feature of the chemistry reservoir condition, the feature of scaling in some of this well. And at those supercritical conditions, it is actually this reaction happen quite quickly. But the key thing is really when you're switching between supercritical to subcritical, that's where most of the reaction happen. So that will help us a lot managing the well, managing our reservoir, and better understanding the connection between the supercritical envelope and the conventional geothermal system, if it is utilized on top already. One of the key aspects is that we want to continue utilizing the reservoir on top, if possible. So it is really important to constrain as much as possible what will be the long-term effect. So what we combine all of this information, and then we did an envelope calculation of what will be the capacity of the supercritical heat envelope underneath the known geothermal system that are non-protected. So this value of the capacity, which is tripling the conventional geothermal utilization that we have now, was really a key to created a message, if you want, for the community and from the government to start looking a little bit more in detail about those deep resources underneath the TVZ. This is not based on permeability. This is purely based on the envelope and the heat. So it's really essential that we will look at drilling. And this is exactly what we're trying to do. So what we've been doing is looking at what is the target. This is what it is. This is, you have a conventional system. We want to target deeper well below a conventional system. And this first instance, around 4 to 6 kilometers. We know based on numerical simulation that some places have likely a supercritical fluid envelope. We need to test really now this capability. And this really what we proposed, and we work with a economic advisement and financial advisement team to put all of this large amount of electricity or capacity that we identified, put this in the context by 2050, in the light of a growth of wind, solar, a decrease of fossil fuel, what will be the potential of geothermal super hot for New Zealand. We can double our geothermal utilization, 19% more if you want by 2050. This was really, really important. But the benefit of working with economists and financial advisor was to look what will be the cost of that. As we know, drilling for geothermal is generally really expensive. What will be the long-term cost? And so here, a cost analysis by 2050, it will be cheaper to invest in geothermal in New Zealand long-term than to overbuild wind, overbuild solar. As we know, for example, offshore wind is also very expensive. We calculated assuming an increase of gas, and we can, obviously this is need to take with a grain of salt. We don't know how the market is going to fluctuate, but we are looking that we can keep the geothermal cost below $100 per megawatt hour of capacity, which is really essential. Those costs are in New Zealand dollars, so that will be around 60 US dollar. So just to summarize, Superhot could provide 30,000 gigawatt hour of sustainable, plentiful, renewable energy to power New Zealand. It could be online with investment by 2037 if we're really pushing. And I want to say online is that the beginning of commercialization, not the exploration. The green model suggests that we can have more than 2,000 megawatts of zero carbon. And obviously, as you know, it's also a very abundant source for heat and off-grid industrial use. All of this information was put into a documentation from minister, government, the energy panel, energy planners, and all of that in the last year. And we have been proposing a different well location and different what could be the optimized drilling that we could propose as a new phase of geothermal exploration. With the first one at the top, I would say, of a shallow intrusion. Then the second one is to test the condition really at the boundary a little bit deeper. And the third one is really, can we unleash the entire heat that is exceptional underneath the topovolcanic zone? There's a de-risking stage, a bit associated with phase 1, 2, and 3. as you can imagine, and learning curve exponential along the way. We are at a point right now where we really needed to learn by drilling what are the conditions, the geophysical, petrological, all the investigation that we can do right now have some limitations. So to prove if it is viable, we really needed to drill. And that is why the New Zealand government was fantastic in supporting this initiative and ring-fenced $60 million last November to drill this first exploration well. There's $5 million released now. It's mainly for design to have an international and a national technical group that will design the deep well adapted for New Zealand condition, an international advisory group or what is the best way to do this. But it's also, we also want to collaborate internationally with the research and with the industry sector to ensure that it is an international success as well. I think the geothermal community really need a success in that space. So been working really closely, particularly with the US and Iceland, to ensure that we have a really good collaboration around that for the future. But it's a very exciting time. We haven't had a government exploration in geothermal for more than 40 years in New Zealand, and it sent a really strong signal internationally that we are back on the innovation and back on finding some geothermal solution for the international community. And with that, thank you very much. Kia ora.
Thank you. Thank you, Isabelle. And congratulations, by the way, on getting that $60 million funding. I imagine it was a culmination of the years of work that you've done.
Yeah, it was quite a challenge, and it was quite, but it is, you know, when you are a geoscientist, it is really essential that we are able to convey our scientific finding into some real solution. I think we don't have the time to just wait for someone to take our result, and the industry needs some guarantee and needs some de-risking to be able to invest in this expensive endeavor, I would say. So it's sending a really strong signal, and again, it's not just me, it's the entire New Zealand community.
Okay, questions are coming in right now, and for everyone in the audience, just feel free to send in your questions. I also have some questions of my own. So there are other countries that are working on supercritical geothermal right now. There's some effort in Iceland, there's some effort in the US. I guess what makes New Zealand different is that you already have operating fields in the same area that you're also looking into supercritical geothermal resources. So what is the strategy for utilizing, or rather are you going to drill into areas where you have operating fields, therefore you have more data, or are you going to drill into more unexploited sites?
So there's several points of that. So the key thing, yes, we are looking, and I've been collaborating along the last 5 years with learning from Iceland, exchanging what they're doing, and US as well. It was really good to see the new DOE project on super hot rock in Newberry. Very exciting, and it's putting all of this knowledge together that will give us and give internationally some success in that space to help with the energy transition and to create a base load source of renewable, which is really important. The first well, to answer the second point, will be in a already utilized geothermal system. It is because we have so much more constraint on the shallow system. We have already all the infrastructure at the surface. There is a know-how in New Zealand. The New Zealand community has been a bit shy in communicating about their technology innovation, and that because honestly they didn't need to. But there's so much knowledge in New Zealand in operating at those already quite high temperature. You know, some of those fields are operating already above 300 degrees. So there is a wealth of knowledge that could be acquired. But the beauty of New Zealand is this large heat source that is really unique. And it's not a lot, there's not a lot of geological setting that way. So it is, and it is quite shallow. So that means you can reduce the cost of drilling. You don't need to drill at 10 kilometers to find those super hot rock condition. You can drill anywhere and you will have super hot rock condition probably anywhere in the topovolcanic zone, and you will have a super hot rock condition. So it is a way as well to limit some of the investment. And it's a great example of international laboratory for developing this technology in collaboration with other geothermal countries such as US, Iceland, and Japan.
Once you have built three exploration wells in site, do you expect the operating site to be operating as normal?
While we're drilling or after?
No, I mean possibly like during testing or something.
Yeah. So we do not want to limit, particularly with the first well. It will be with the sector. It has to be. First of all, because you need a fast adaptation. It's not a scientific drilling. It is actually a drilling for a purpose of commercialization. And that's why we're trying to put everything in place to have a success. So we're looking with some individual, some companies to see how we're going to manage. And then once we have a condition, it would be a lot easier to better understand what will be the effect of the reservoir, and if not. The connection is really important between the two. It depends. There's several models that say that there's a connection between the supercritical envelope and the shallow system. In New Zealand, those are hard to assess right now. From numerical modeling, it seems that it's fully connected. We do not have a carapace, but again, this needs to be like really at the point we need to check that drilling right now. We do not want to interfere with I would say the electricity generation, the geothermal electricity generation in New Zealand, as we need to continue providing electricity to the grid using geothermal. So it's really, that's why it's need to be the utilizer, the generator will be definitely partner in that.
Some of the questions from the audience, some very specific questions. What pressure and temperature are you expecting at the wellhead?
Oh my goodness, I should have checked my numbers.
Okay, this one might be a little less specific, but yeah, what kind of casing program?
Like those conditions, sorry, it will be, I wish my colleague, I am not a geothermal engineer, so if this is a condition. The temperature that we're expecting is around 400 degrees, and the wellhead is at the maximum of what we have now. I think it's around 60. So but it needs to be, if you want some information, I advise everyone to go and look at the Geothermal Next Generation website, where all of this information is released. And we did some supercritical well modeling and design based on what we know of the condition of engineering condition that we had, I would say. So with design. So all of this information is available. I just don't have it on the top of my head right now. I should have opened them before. Very specific question, really good question.
Yeah, I know, that's fine. Okay, something that is a little less specific but also important. Any idea of what kind of casing program is planned for such a well?
Yeah, so the casing is really one of the challenge. Drilling is, so if you're looking at very recently, the Clean Air Task Force has been releasing a series of reports around designing this type of well, and following some conversation that I had with some international group, the drilling is really not that challenging and it's not too much of an issue. But the casing, it's really the thing. And that's where there's a lot of work already happening in Iceland, in Europe, There's been some program. So this is clearly why the first $5 million are really the key to gather all of this information and to design as simple as possible a well that will sustain those conditions. I'm not a casing expert, but that means that looking at what will be the best cement concrete condition, what will be the best steel condition for that. We do know that at supercritical condition, casing is the main thing that failed in the past in Iceland or in other places. But it's really important to say that there is the fact that we already drilled it and we identified where are the casing failure, particularly at the junction of the casing. That's really what is important to solve. So that's why we're going to have a team of some of the best well designer, if you want, to work on us. And people not from engineering school are not, looking, people that are actually used to drill at 300 degrees, people that are used to do well that are actually really powerful in New Zealand. We have already some well that can sustain a really large amount of energy. It's one of the beauty of New Zealand. Like our well output can be around 30 megawatt, which is incredible. So we are already quite advanced in the design. And internationally as well, the code is for design it's still following some of the New Zealand guidance. So it's really it's going to be a challenge. I do not know yet, because this work just starts, what will be the specificity of the cement, the specificity of the steel that are going to be chosen for this well. And obviously that's why this is not a work that we can do. We need to rely on the sector for that. And that was very important to leverage this type of money to be able to design that.
Good. Other questions? You did mention earlier that the part where the part where the well transitions from supercritical to subcritical is kind of a very important spot in modeling. So what kind of processes are you expecting there? What kind of chemical reactions should we expect, or what kind of, say, change in phase do we expect at that junction?
So when you are at just the juvenature of the supercritical fluid, there are there's less total dissolved solid in a supercritical fluid. But when you have the phase transition, so when you're cooling down, that's where you have a lot more of solid going into the liquid phase, right? And all the super hot, like at the supercritical condition. This implies at those conditions, the chemical reaction with the rock are extremely fast. So that means that you will, if you're not drilling in the supercritical condition, you will drastically, you can utilize, but that means that any reinjection technology or anything, you will cool down the system and you will scale quite quickly. So it is really important to maintain those conditions. The reactivity as well of some of the supercritical fluid in terms of corrosion are actually quite intense. And so the design of the steel is very important. But constraining those, there is also a pressure change when you're passing through supercritical to subcritical that will need to be taking into account where if the transition happen in the well. So in the design, you really need to take care of the potential expansion or reduction that you're going to have, the contraction of the well, this type of thing that needs to be designed. But constraining those reaction were really the key thing. That will also help us design the best use of those super hot well, if you want. There is a new program, for example, in Iceland, which is very aligned to ours with volcanic energy, where they actually model and they are testing for re-injecting those conditions to utilize in the conventional system. And they're showing that you can stimulate the shallow well. So it's really, but we can't do this without knowing the condition we have down. And I was really, it's really important that we're getting this information. And that's potentially, but understanding how you will be able to re-inject in this supercritical condition and understanding what will be the reaction, the kinetic of this reaction is really understand the behavior of your alteration front, if you want, in your reservoir.
You already kind of touched on this, but there's another question here about permeability. So I suppose that you're potentially drilling into a brittle ductile transition layer, and so what kind of permeability should we expect when we get down there?
This is the $1,000,000 question, isn't it? So permeability and heat, and I'm always teasing my geophysical colleagues, are the two things that we can't image directly. And it is the cornerstone of geothermal utilization. Permeability condition, and that's why the capacity that we had is purely the numbers, is purely on heat, because our heat output, or because you don't know what the permeability will be. There's some really interesting new experiments that show you have actually intrasec microfracturing and permeability in the brittle ductile transition. So when you're passing a ductile, but drastically, generally, when you're passing your brittle ductile transition, your permeability decreases massively. So the aim is to go right above it, where you know that those deep fluids are heated. We already know we have some temperature above 400 because we're losing some of the organic tracer in New Zealand in some of the sites, and so that are not stable above 400 degrees. So we already know we have those conditions. So that's mean that some of the fluids are circulating at greater depth. But assessing the permeability, and that's where the limitation of some of the numerical modeling is happening. No offense to any numerical modeling online, I absolutely support your work, but it is also a very simplistic reality, if you want, that you don't have all the in and out of how fluids circulate in the crust. New Zealand is extremely active. The topovolcanic zone is riddle of active faulting, plus the magma. So the link between the active faulting, the fracture of the Grey-Waikiki, which is because of the metamorphic work, there is already a lot of fracture and a lot of veining that can be reactivated, that can be used, that can be permeable. It's really hard to understand what will be the condition that we will have. But the permeability is, the modeling show that we should have a supercritical envelope. Obviously, it will be tested. We know that there is some fluid circulating at those conditions. So we just need to make sure that when we're drilling, we find them.
So the drilling strategy is kind of similar. So you're still targeting fracture controlled permeability.
In New Zealand, if you are in the basement, it's most likely it will be, because the volcanic cover, the permeability in the lithology is really limited to the volcanic cover, and when you have very porous, like pumice and volcanic clastic layers, and that's fantastic because that brings the meteoric water really deep in the crust. I mean, and there's some sites where you have those volcanic deposits on kilometer scale. I mean, we haven't found the basement in Waikiki geothermal field, for example, and we know we are drilling down to 3 kilometers. So the amount of volcanic product that can facilitate the penetration and the infiltration of water is essential. But if you're going at greater depths, and that's why looking at the gravity and looking at other geophysical metal to identify where the basement limit was beyond the drilling that we know, was really essential. But yes, there is very limited intrasec permeability in the Grey-Waikiki, so it will be fracture control. It's the role, there's two aspects as well, is that we do not necessarily understand as well the balance between the fracture network that is intersect into, and the connectivity between those fracture and the basement, and the fault. So there's a lot of faulting that influence drastically the hydrothermal circulation at shallow depths. It's been well recorded. And when I say fault, it's also caldera margin. It's not just the normal faulting, but there is more than, in the volcanic record, there's more than 28 caldera forming events in the topovolcanic zone. So you can imagine how much of a jigsaw puzzle it is down there that no numerical simulation can simulate. But it is really essential that we constrain by drilling the type of permeability we're going to have. We are also planning in the future to do some high temperature rock property measurement at those conditions to try to see if you have an anisotropic rock, such as the greywacke, what kind of permeability, because most of the experiments that exist are made on homogeneous greywacke granite. So we don't know when you have a rock such as the greywacke, how that will behave at those conditions.
You did mention that you already have a supercritical reactor, right? You have the facility for testing this. What have been the results of studies on, say, fracture behavior in supercritical conditions?
So it's an experimental geochemistry. It's not a rock property lab. So it's experimental geochemistry lab. We don't break rock. So we rely on some analysis from there's some been done in Japan, some been done in Lausanne. So we do not have those facility in New Zealand. So our work, and it's also a legacy in New Zealand. We've always been very strong in understanding geochemistry of geothermal of fluid circulating in geothermal system, and we're continuing really this legacy. So the experimental lab that we have can simulate from 0 degree to 700 degree at various hydrostatic pressure how the rock will interact. But we don't look at how, if you are putting the rock under pressure, how that will, affect. So just to make clear that that's what the facility we have. And there's really not that many in the lab that do that in the world that have those geochemistry. Same thing for the rock properties. So we're relying a lot on international collaboration for that.
We have very unusual question, but what is there any potential for lithium extraction from supercritical geothermal fluids?
It's not at all unusual. It's not just lithium. If any, is there any critical elements that could be extracting from geothermal as a whole? And there's a lot of interest into this. There is a lot of potential from direct extraction from fluid in the crust of critical element. Based on the nature of the supercritical fluid and the fact that there is less total dissolved solid in it, we do not anticipate that there will be more metals, if you want, in the fluid. It is really important to make the distinction that we are not targeting magmatic fluid that are exsolving from magma directly. We are targeting the base of the hydrothermal meteoric cell. So the more dilute, and it's a really it's a very strategic thing. It's because if you're targeting magmatic fluid, you're going to have a lot of total dissolved solid and a lot of chlorine and a lot of acid, so a lot more problem during the utilization. New Zealand has some potential for critical element in other place, more in conventional system. It's still very dilute fluid in New Zealand because we had so much groundwater circulating. So we do not expect to have a lithium, in-situ lithium mining for those supercritical wells.
Yeah, and so that also kind of clears up your approach versus what is happening in Iceland, because Iceland is deliberately targeting magma-influenced fluids, right?
Yes and no, because they do have a different magma type. They're still targeting fluid that are not necessary. They're mainly meteoric fluids still. I think the biggest difference in our targeting is with Japan, where they are voluntarily going to drill into the top of, if hopefully if they are doing drilling on the top of a magmatic intrusion that shows some high salinity fluid. that are clearly magnetic fluid. So that's the difference. But Iceland and New Zealand share a dilute fluid system. It's also because they are dealing with basalt, and they're on mid-ocean ridge and hotspot zone, which is there's definitely less chlorine in the magmas. There's less degassing. There's a lot of CO2. But there's not as much metals transport and chlorine ligand, if you want, metal that are transported by chlorine ligand. So it's in arc setting, it's a little bit different. We need to be careful around where we're targeting. But that's really the key thing. I think Japan is the biggest difference. They have some sites where they do want to drill into magma. There's also some more target work actually for metal extraction on deep geothermal in I think Montserrat has some as well. But it's not the case in New Zealand. We do not want to target magnetic fluid because it's just going to be even harder to utilize those systems. So why will you go where it's going to be harder to generate electricity?
Yeah, a question here on geochemistry, since you mentioned that it's kind of the strength of New Zealand, understanding geochemistry, geothermal system. So how does your modeling so far change our understanding of geochemistry? Are we going to propose new models for solubility of silica and anhydrite, as you mentioned?
Yeah, so the key thing was the base of understanding the processes that are happening in just like the solubility that are essential. I mean, all of the turf react models and things like that have some limitation of just first of all, the equation of state of water, and they're limited in the amount of solid that you can put in it. And they have also the limitation of just the solubility value that need to be, some of this experiments are from 1950s. So it was really essential to just get this baseline knowledge. We don't expect that we're going to drastically change, or maybe we will. That would be fantastic. It's still water rock interaction and it's still geochemistry. But the more we're refining, the better we can utilize efficiently, the better we can have a reservoir management that is appropriate. It's often like we also often think about, and particularly we often think about, the rock mechanic, the fracture, how you circulate fluid. But as soon as you're putting heat into water and you're putting this water into a rock, you have reaction. So even when you're thinking about a super hot rock system, a DPGS system, you're going to have to take care of your quartz solubility. You're going to have to take care of your calcite solubility, your anhydrite solubility, all of those type of things. So being able to model this accordingly was absolutely essential, and having some fundamental chemistry data that can be used by the chemical engineer. And that's what's really the strength. But to be able to do this, we really needed to invest into this one-of-a-kind lab. And it's because there is other lab that can do the rock properties, that's this investing in geochemistry was really essential.
I imagine it's our understanding of geochemistry right now took decades, right? So it's going to be the same magnitude of work, I imagine, to understand supercritical geochemistry.
Yeah, it was. I mean, we're having a really good start. Iceland, with Anders Stephenson group at the University of Iceland, is already also making a bit collaborate result, which is really good when you have two different labs showing the same thing. So they are like really advancing as well some of its understanding. But it's also very important. The more we actually utilize, the more we're simulating the natural world, the better we can manage. And in the future, we're already helping some of the just in conventional geothermal system to better understand injection, to better understand the reaction path in the rock. So all of this, if you want the time of a reaction, the scaling that you have on the rock when you're re-injecting or when you're operating, you can actually take that, and then numerical modelers that are specialized in chemical transport modeling can do this. And really the next stage is to put this into a thermomechanic chemical modeling. And there's few teams that are developing that, but you need the computer power, you need the equation of state, you need the new coding. And at Supercritical, we are just at the beginning of that, because we just didn't have the computation power. Like, it's really at the fringe of some like just the scientific knowledge that we have about that. So it's very exciting. But again, it's knowing what we have down there will help drastically reduce the risk and reduce actually we will be able to do some modeling and to do some computing that is fit for purpose, I would say, instead of having more processes and more schematic diagram, more close to reality.
I find that very exciting because improving our understanding of thermodynamics in supercritical conditions has applications beyond geothermal.
Yeah, 100%. I mean, there is already quite a lot of knowledge from supercritical pure water because of thermal power plants that utilize supercritical pure water. But it's very, you can apply some of the thermodynamic for that, but we need to bring it to the real world, and it's coming with a lot of challenge. And the more, it will go at the same time than what we learned, 60 years ago about depressurization and hydrothermal front and all of this type of thing. And it's geothermal. I mean, we have a lot of understanding about the chemical reaction that happen above magmas and based on fossil systems that have been utilized for mining and things like that. But it's always fixed in time. And the fact that we can actually understand the dynamic of how the hydrothermal circulation happen with the chemistry, the pressure, it's such a advance, I would say, in the understanding of this connection between magma and the hydrothermal system from a more, I would say, academic point of view. But it's really what I like about what we've been doing and what we're continuing doing is utilizing this incredible growth in academic knowledge for a very fit for purpose output. And it's really to deliver some solutions that are really needed and really fast. So it's really, it makes it, I'm very proud of the team. Let's just put it that way.
I'm also very excited. I think that learning how to utilize supercritical geothermal resources might have the biggest incremental effect on the growth of geothermal worldwide.
Well, I'm not going to say no. It's just, I think it's on the growth. Let's just put I'm a huge buyer, as you can imagine, but let's just put a kind of, it's really important to say that this is one solution. It may not be fit for purpose for every country. It's one solution that will be aligned with the growth of wind, the growth of solar, the growth of biomass, the growth of e-fuel, hydrogen, all of this type of thing, right? But the key thing about it's a solution for, it's the only source that we have that is not fossil fuel based other than nuclear for baseload, for constant electricity generation. And I think that there is an appeal to that. In New Zealand, we will never see nuclear. So it's really, we literally had no choice. It's really putting all of this knowledge towards a end goal that the society can utilize. I think it's not necessarily what brought every geoscientist, but it's the power of working as a multidisciplinary community towards a goal that serves everyone.
Okay then, and I think that's the perfect note to end the webinar. Thank you for everyone who stayed on. Thank you for everyone who attended, and I'm really looking forward to the first well for supercritical geothermal to be drilled in New Zealand. I hope it's soon.
Me too. Thank you very much. Thank you, everyone.
Thank you, Isabelle.
Thank you. Bye.
Bye, everyone. Happy weekend.
Bye.